So this week, this is the last chapter we'll cover this week. Factorization. In this section, you can always assume, unless I tell you otherwise, that any ring is an integral limit. So it's a commutative ring with identity, no non-zero, zero divisors. Definition. What are a domain? I'm going to attempt to define an important kind of element that you see in integral domains. Actually, two types. A non-zero one. Let me ask you this: how many? Somebody tell me what your definition of a prime is. What's the folklore that you've heard around campfire? What's a prime integer?
Something that it only has one in itself that divides.
And is not one, right? How many of you have heard that? Only one in itself is a divisor. We're going to mimic this. A non-zero non-unit pi in R is irreducible. So I can't break it down any further. If pi equals AB implies A or P is a unit in R. This is the way I would generalize this. This sort of says if you can factor it, one of the factors has to be a unit. So in the integers, what that means is if you factor, one of the factors has to be one. Right? So this is kind of the old, its only divisors are itself and one. Right? It's the MO of that. Has anybody ever heard another definition for prime? How many of you have heard this one? A non-unit, well, I don't want it to be convertible. P and R prime if P divides A times B implies P divides A or P divides A. Has anybody ever heard this definition of a prime? That if it ever divides a product of two things, it has to divide one of the two. This is really the proper definition. These two notions are actually different. Right? In the integers, as long as you throw out zero, these are the same in the integers. But more generally, and I'll give you some examples, it bifurcates, they can be different. So here's an example. So we were talking about polynomials last time, virtually. In the polynomial ring Cx, so this is polynomials with coefficients in the integers. I'll give you some examples here. 2x, 1 plus x are all prime. In any integral domain, zero prime. Now, if you go through the definition carefully, you'll see why this is true. Suppose zero divides a product of two things. Well, can zero divide something? Actually, it can, right? Because suppose zero divides AB. What does this mean? Literally, this means that AB is equal to zero times some R in R, right? So that means that A times B is zero, right? And if it's an integral domain, what does that mean? Either A or B is zero, therefore one of those two is. So in a strange way, zero is in fact prime. Zero in an integral domain is never irreducible, right? Because you can factor zero as zero times anything, right? It doesn't have to be a unit. In the power series ring, I'm going to look at these elements again. Two and X are prime. 1 plus X is not. Do you know, anybody know what? 4 plus X is a unit. So it can't be. Yes.
So why is 1 plus x of prime and z of x?
I have not explained that really yet. This is just an example. I could go through it and show this by definition, but it would be tedious. I'm gonna give you some stuff later that will make this clearer, right? But 1 plus X is a unit because if you just continue this, it's 1. So that strange power series is inverse. Here's another example, and again, I'm not going to prove that this is true, but you're going to see something like it on the homework as you work this out. And I'm going to give you another example. It's a little clearer to see. If you consider this ring right here, this is all complex numbers. A plus B square root -5, or A, B are integers. Notice this is a integral domain. It contains the integers. The elements 2, 3, and 1 plus or minus square root -5 are irreducible, but not prime. This ring does contain some primes, though. For example, it contains 0, and as it turns out, the element 6 plus the square root of -5 turns out to be prime as well. Right? You might see if you can verify that. But I'm going to give you a better example. I'm going to give you some. Here's another example of the contrast between irreducible primes. Let's let R be the ring. I'm going to call this here's what I mean by this notation. This is a set of polynomials that are sort of missing the linear term, right? So the coefficient of the linear term is 0. So what does an element of this look like? A0 plus A2 x squared plus A3 x cubed. And you can have any power after 2, you just can't have the first power. Right. So it's all polynomials that are a little bit crippled. They're missing the linear term in a certain sense. What happens if you add 2 polynomials that are missing a linear term? You get a new polynomial that's missing a linear term, right? And if you multiply 2 polynomials that are missing a linear term, there's no way to make a linear term in that product. So this is, in fact, an integral domain. This is a subring. This is a subring of all polynomials. Now, let me point out that x squared is irreducible. You can't factor that down unless one of the factors is a unit. So let's kind of talk our way through this. Let me ask you this. X squared, polynomial, what's the degree of that polynomial? It's 2, right? Good. If you can factor it into a product of 2 polynomials, what do the degrees of the product have to be? If you could break down x squared, it's of degree 2. It has to factor into what? What are the possibilities?
To add up to 2.
Right, right. So you got 2 choices, 2 degree 1s or a degree 0 and a degree 2. Agreed? And those are both bogus because you can't factor this into 2 degree 1s because there ain't no degree 1 terms at all. So you're stuck there. And if you factor it down into degree 0 and a degree 2, that means that one of the factors has to be a constant. And all the constants are units because this is a field, right? So if you factor x squared as 2 times 1/2 x squared, that 2 is a unit, right? So this is irreducible. Everybody agree with that? So is x cubed. Now, x to the 4th power isn't irreducible because I can easily see how to factor that. X squared times x squared is x to the 4th, right? But x cubed is irreducible. It's a little bit more complicated, but it's the same argument as before. You can either factor that into an x3, or I'm sorry, a cubic times degree 0, in which case the degree 0 is going to be a unit. Okay, so you can't do that. The only other way you can do it is a degree 1 and a degree 2, or vice versa. You need a degree 1 and it's not there. So x cubed is irreducible. Now, I am going to use this to sort of do a double example to show you're used to things like in the integers, everything factors uniquely into. This does not happen in this particular integral domain. Look at the element x to the 6th. I'm going to factor this 2 ways into irreducible. Not only are there 2 different factorizations of x6 into irreducibles, they're not even the same length. This one factors into 3, this way factors it into 3 irreducibles, and this only 2. Let me point out also that this example makes it easy to see that, for example, x squared is an irreducible, it's not prime. Why is x squared not prime? If you look at this part of the equation here, x squared, I think we can agree, divides x cubed times x cubed, right? Because this divides into this, and the quotient is x to the 4th. Agreed? X squared divides this product, but it doesn't divide either one of these. Because if it divided x cubed, there'd have to be a linear, and there isn't, right? So this is a good example. Both x squared and x cubed are irreducibles. They're also not prime. And you see that we have factorizations here that not only can they be different, they can be of different length. Now, trying to sort of divide out what's irreducible and what's prime is actually kind of an important thing. And I'm going to, so what's a prime mean? It means it's a non-unit, and if it divides the product of 2 things, it has to divide one of the 2 things of the product. Here's the most compact and universal, this is equivalent to what we're saying, definition of prime. And this is why we studied ideals, because the notion of prime has a very good way to think about it in terms of ideals in the following sense. When 11.14. Let x in R be a non-unit. I guess it's an order prime, so I didn't say that technically. Then x is prime and R is a domain again. X is prime if and only if the ideal generated by X, principal ideal generated by X, is prime ideal. And this is really actually the best way to define what the problem is. Let me go through this. And this proof is not difficult, but it sort of illustrates when you talk about ideals, containment is similar to vision. So let's go this way. Suppose X is prime. So we know that if X divides the product of 2 things, it has to divide one of the 2 things. We want to show that X is a prime ideal. So let's let A times B be the ideal generated by X. right? What does this literally mean? Well, the ideal generated by X are just all multiples of X. So this means Rx for some R and R. Right? Well, remember X is prime, and this equation right here means that X divides AB by its beautiful primeness. This means that X divides B. X divides A or X divides B. This is equivalent statement. X divides A or X equals, I'm sorry, B equals X B prime. And this is equivalent to A and X or B X. So X prime. So we've shown that if the element X is prime, the ideal generated by X is prime, and the converse is just almost doing this reverse. So now, I'll go through that detail here. On the other hand, if you want to truck it on back, we want to assume that the ideal generated by X is prime. And suppose X divides AB. Okay. Well, this means this is going to look very similar here. X divides AB. AB is RX. So R and R. That's what it means for X to divide AB, which is equivalent to AB is in the ideal generated by X. Since AB is Rx, that just means A times B is in the ideal generated by X. But I know that the ideal generated by X is prime. So A is in the ideal generated by X, or B is in the ideal by X, which is equivalent to A equals A prime X, or B equals B prime X. Therefore, X divides A, or X divides B, and X is prime. So let me give you kind of a neat little spin off this. This theorem shows that an element is prime if and only if the ideal that it generates is prime. This makes it much easier to see that zero is actually a prime element in an integral domain, because we already know that the zero ideal in an integral domain is a prime ideal. Okay. Any questions on it? Okay, here is a theorem, and this establishes we've already seen an example, actually a couple of examples really, of elements that are irreducible, not prime, right? How about the other way around? Well, actually, prime is the stronger notion. So if you have any prime that's irreducible, as long as that prime is not zero. Zero is kind of defective, right? Because zero can never be irreducible. Theorem. let R be domain if P is a non-zero prime. And R, then P is irreducible. So why did your teachers spend years telling you that what a prime is its only factors are itself and one? Well, one of the things that you probably remember about the integers, one of the first things is it has the fundamental theorem of arithmetic, right? Every non-zero non-unit in the integers, you can factor it uniquely into primes up to a sign. Everybody remember that? It turns out that in any integral domain where you have the fundamental theorem of arithmetic, that is, everything can be factored uniquely into primes, the notions of irreducible and non-zero prime are equivalent, right? So in a certain sense, when your teachers told you this is what it means to be a prime, they were sort of wrong in a sense because it's really irreducible. But they got lucky because they were probably talking about the integers. And the integers has unique factorization, which means as long as we're not talking about zero, primes and irreducibles are the same thing. But this is only in domains where you have the fundamental theorem of arithmetic. In general, I expect prime to be stronger. So this is what this says. If you avoid zero, throw zero out of the mix, any prime is an irreducible. Let's prove this. This is fun. Let and I bet we're going to see where my assumption that this animal is not zero comes up. I want to show it's irreducible, right? Suppose, please, yes, I'm going to regret this for the rest of the class. So, suppose is equal to A. I want to show that either A or B is a unit, correct? Well, if I have this equation, I think we can all agree that this means that P divides A times B because it's equal to A times B, so it has to divide A times B, right? Now, what do I know about P? It's prime. So that means it has to divide one of those two, right? So without loss of generality, it has to divide either A or B. We'll say that P divides A. At about one, and I'll say about that. So this means that means that A is equal to PA prime, sum A prime. Now, what I'm going to do is I'm going to take that A and I'm going to shove it back into this equation here. So I have P equal to AB, which is now equal to PA prime. Agree? A, I'm going to be super careful of this. All I did is I brought the P A prime B over to the other side, and then I pulled out a P, right? This is a product of two things, P and this other thing, and we're in an integral domain, and their product is zero. That means that either P or 1 minus of A prime B, zero. But P is not zero. That's key right there, because actually my proof kind of implodes if I'm not under that assumption here. This means so that means A prime B equals 1. Therefore, P is a unit. So P is irreducible. Because essentially what we've shown here is if I factor P into A times B, if A is not a unit, that is, if P divides it, then the other piece has to be a unit. Okay. Well, that's just. So, let me give you a definition. And I'll kind of give you a little history behind the terminology. Well, definition. Eleven one six. You say the domain R is atomic. Well, what does it mean for domain to be atomic? If every non-zero, non-unit of R can be written as a product of irreducibles. So the terminology for atomic, what this means is if you have any element that's not zero and not a unit, you can factor it down into a smallest form in a certain sense, where you can't break the factors down any further. These irreducible. So everything that's not zero and not a unit can be factored into irreducible elements. And these elements are sometimes called atoms. You see this also in terminology. Atom equals an irreducible element. Yes, I'm sure this came through, people said, oh, look, mathematicians that didn't do so well in chemistry, they thought that the atom was the smallest part that you couldn't break down any further. No, we'll not have a physics chemistry argument about this. And I guess atomic sounds better than irreducible or something. But anyway, this is the terminology here. Now, what kind of domains are atomic? Well, at this point where you all are at, probably everything you can think of. Right? Let me give you some examples. A field. What are the non-zero non-units in a field? Nothing, right? Because everything in the field is either zero or it's a unit, right? It is vacuously atomic. The integers, right? Everything can be written as a product of primes, other than plus or minus one and zero. That is atomic. The ring that we polynomial rings and any number of variables. Well, let's see, Z, ZX, polynomial ring and 3 variables. That's atomic. In fact, a polynomial ring and infinitely many variables, also atomic. That ring we just looked at, the one that had the irreducibles that were not prime. This thing was missing, that's atomic. In fact, let me ask you a question. Here's the harder thing is, can anybody think of an example of a ring that's not atomic? This one at this point might tickle the imagination a little bit better. Can you think of something where you think of a structure where you can keep factoring and you can keep pulling out stuff, no matter what? It never stops factoring. Yeah.
Zero ring?
Oh, man. Well, you sort of got me back. So let me, how about an integral domain? This is a little harder to come up with. Let me give you a couple of examples. I can give you two of them that are, but they're not easy examples, really. Here's the first. This is the set of polynomials. Now, let me point out the silliness of this example in the following sense. Okay, so what do I mean by this? These are all polynomials that have rational coefficients with one exception. I demand that the constant term be an integer. All right. So you can have any set of coefficients for your polynomial. It's just you got to have an integer as that constant term. It's fairly easy to see this as ring because when you add two things that have an integer constant term, it's still got an integer constant term. If you multiply two things with an integer constant term, same thing, right? And here's the frustrating thing. If I change this z to q, so if instead of just letting this be integers, if I let it be all rational numbers, not only is this atomic, but it's got the fundamental theorem of arithmetic. Everything factors uniquely into primes, but this one, it's not atomic. Does anybody see anything in there that can't be, that you can always keep factoring something out of? It never stops? How about X? But Jim, you're on drugs, right? That's degree one, right? How in the world could you ever factor stuff out of this? But you can. You can factor it. Give me your favorite prime, not zero. Everybody's got to have a favorite prime. 3. Watch this. X is not irreducible anymore because 3, when I pull that out, I've got its quotient in here because I'm allowed to have rationals adjoining the X. So this is 3 times X over 3, right? This is useless if I allow this to be rationals, then 3 would be a unit. But 3 is not a unit here because in this ring, there is no 1/3. So 3 isn't a unit. And you know what? I can go crazy with your example. Look, I can just do this all day long. And there's nothing special about 3. This is not a proof. I haven't really proved it, but if you look at the monomial X, you cannot factor it into irreducibles because no matter how you dance around, there's more you can pull out of it, and it never stops. Right? There are a lot of things in here that can be factored into irreducibles, but X isn't one of them. How about this example here? Now, really, to do this one up properly, which I'm not going to do, I'm just going to give it to you kind of like a folklore example. I'd have to go through this. This is the set of all complex numbers. C is a root of a polynomial of form x to the n plus m sub n minus 1, x to the n minus 1. plus M1X plus M0 with Mi. So my polynomial actually has a specific form. It has to be monic in the sense that the coefficient of the highest degree term has to be 1. And the rest of the coefficients are integers. Well, anything you want. Now, so for example, what is in this ring? Every integer is in it because every integer is the root of x minus whatever that integer is, right? 2 is a root of x minus 2, right? But this has got a boatload of other stuff in it. Let me name some other stuff that's in this ring. The square root of 2 is in here. I is in here. All 5 roots of the polynomial, all 5 complex roots of that polynomial are in this ring. Now, what's not clear at this point, what I haven't developed for you is the following. It's not even clear that this is a ring, right? If I take a root of some polynomial, root of some other polynomial of this kind of general form, is its sum the root of, is its product? And the answer is yes, right? But that's beyond what we have time for here. But this is a ring and it's called the ring of all algebraic integers. This ring is called an antimatter ring because it has no atoms at all. And the reason is if I take any element in here, its square root is in here. So it's impossible for anything to be irreducible because take any element and it breaks up into the product, the square of its square root. In fact, it's not just square root. Any element in here has every nth root in here, right? I can break it up into 3 of its cube roots and so forth. This was crazy because most of the elements in here are not, this is far from being a field, but there is no irreducible in here at all. Whatever element you take, it breaks down. In the previous example, there are irreducibles, like 3, for example. And this one, there aren't any at all. Okay, any questions? Yes.
If you change in the first example, if you change the Z to Q, why would that make it atomic?
I'm going to have a theorem that tells us that. But the reason that this example no longer works is see how I screwed things up with this factorization here? If that were a Q, I've done nothing because this is a unit, right? But in this ring, it's not a unit, right? So I've actually done something non-trivial. Pulling a 3 out if there was a Q there is the same thing as pulling a 1 out because you've got a 1/3 in there, right? No 1/3 in this one. Okay, other questions? Okay, so now that we've talked a little bit about irreducibles, primes, and a little bit about factorization, I'm going to talk about 3, well, probably the big 3, as far as integral domains that are sort of factorization types. All 3 of them construed as generalizations of the integers. How many of you have heard any of this terminology? UFD, PID, Euclidean domain? So okay, yeah. Here's what a UFD is. So I'm going to take these apart piece by piece. Perhaps I'll start with a UFD means unique factorization domain. What is that? That is just a integral domain that behaves like the integers in the sense that it's got a fundamental theorem root. A UFD is a generalization of the integers in the sense that every non-zero non-unit can be factored uniquely down into primes. All right. A PID, you probably actually have heard of that from the homework. PID means a principal ideal domain. What does the ideals got to do with it? Well, we'll see, because actually a PID is like a UFD on steroids. Every PID is a UFD. And what's a Euclidean domain? Well, Euclidean domains are like PIDs on steroids. So, do y'all remember the Euclidean algorithm? Right, we talked about this. you divide one integer by the other, and it either divides in evenly, or you can get it to have a remainder that's smaller than what you divide it by, right? That's the old Euclidean algorithm. That's what a Euclidean domain is. You've got some kind of algorithm that mimics the Euclidean algorithm that you have in it. So there's some way to take two elements, divide one into the other, and get a remainder that is either zero or smaller in measure to what you divided by. So you can keep dividing and getting smaller. There are two places you've seen it. How many of you have seen the Euclidean algorithm in the integers? Right? Probably did. You might have done that way back in grade school. So your teacher might have given you an exercise and said, divide this by 19 and get a remainder less than 19, right? Something like that. There's another place that you saw it, perhaps, but you may not have realized that's what you're doing. So I'm gonna look like I completely had a stroke here. Maybe that is happening. How many of you have ever done something like this before? What do? How do you do it? Remember? Actually, I could probably do this just straight up. Yeah, you could do a trig section straight up. But what's the technique that should maybe when you see a quotient of two polynomials? Partial fraction. Right? And what's the first thing you do in partial fractions? You look at the degree of the bottom and the degree of the top. And if the degree of the top is at least as big as the degree of the bottom, you got to divide first. Y'all remember that? So let's see what happens. If I were to do this, I would say, oh crap, the top is bigger than the bottom. So let's go through that. Let's see. Let me hold my places here. X4 plus 0x cubed plus 0x squared plus 0x plus 1. That'll just, as I do have a flair for the dramatic, but that is just there to kind of help me keep my place, right? How many times does x squared go into here? X squared times, right? So you get x squared plus x squared, x4, there we go, plus x squared. And then what do? You subtract, just like in the old days, if you're doing long division. You subtract here and you get 0. This minus 0, that's all 0. You get minus x squared plus 1, right? And now I guess that goes in what? Minus 1 times? So it's going to be minus x squared minus 1 x prime. Right? And what happens now? Well, now it's like, oh, well, this is of degree 0, and this is degree 2, and it doesn't divide anymore. So really what you've got here is that remainder 2. And there's a measure. This is actually another example of the Euclidean algorithm. And this is why partial fractions works, right? Because what happens here is I divided this thing into the bigger x4 plus 1, and I did my business. I got a quotient. A quotient was x squared minus 1. And then I got my remainder over what I divided by. When you did that partial fractions rewrite, what you were doing is you were doing the Euclidean algorithm on polynomials. Right? You just divide this into it until finally you get a polynomial down here that has degrees smaller than what you're dividing into. So here, as opposed to when you do the Euclidean algorithm in the integers and you just wait until the remainder is smaller than what you divide, what smaller here means is smaller degree. So let's generalize this. Let me give you a formal definition of what it means to be Euclidean domain. And this is a mouthful, but it's really not that bad. Definition 1.21. We say that R is Euclidean domain if there is a function and again, I'm talking about an integral domain So Euclidean modifies domain. So first and foremost, this has to be an integral domain. If there exists a function, and this is sometimes called the Euclidean norm or just the Euclidean function. This function is defined on everything in R except perhaps zero. It may not be defined on zero. Into the natural numbers union zero. Some authors say the natural numbers, that's fine too. It's just any, you can divide it onto any subset of the natural numbers, really. That satisfies. I wanted to satisfy not just any, a couple of problems. I want phi of xy to be greater than or equal to phi x. And of course, this applies to all xy in my domain. So x and y are just elements of the ring that aren't zero. And number two, here's the Euclidean part. For all x, y, and r, and we'll say R not zero. So for all x, y, and r minus zero, there exists a q and r such that y is equal to qx plus r. What this equation says is it's speaking to you, and it says, okay, look, x divides into y, the quotient is q, and the remainder is r, and my conditions on r are either r equals zero, and that means it divided in there perfectly, right? That is to say, x divides y in this case, or Euclidean size of remainder is smaller than x. Let me give you some examples here. So here's some examples of Euclidean domains. D is Euclidean domain, and phi c minus zero into the natural numbers how about absolute value, right? Because you're just measuring the size of the remainder. These are Euclidean domains. Another one that's important. Field. Another important example is a polynomial ring over a field. If you're not over a field, this is not Euclidean. It has to be over a field. Otherwise, there's problems with division. You have to be able to get all the scalars to divide. Here, this from fx minus zero, the natural numbers union zero, is phi of f of x equals the degree of f of x. Here's another one. Formal power series over. Again, you have to have a field or this doesn't work. Phi of an xn plus an plus 1 xn plus 1 whatever. So in other words, here AN is not zero. If this power series is not the zero power series, it has to have a smallest coefficient that's not zero. This is sort of the opposite of degree. And a polynomial is the biggest coefficient. This one's the smallest one. This is Euclidean domain, and the way you measure it by size is the degree of the smallest term. And here's one more example to think about. This is called the Gaussian integers. It's important in number theory. It shows up all over the place. These are all the complex numbers, a plus bi, where a and b are integers. Here, phi from zi minus zero, natural numbers unit zero, is given by phi of a plus bi is a squared plus b squared. These are all examples of Euclidean domains in the normal function that goes with them. We'll talk more about this next time. Any questions? All right. Well, don't forget, I sent you all an email. If you want me to be here afternoon today, please come and give me a personal request or send me an email because otherwise I'm going to go.